Hello YouTube, my name is Aviv and today we're going to be talking about GANs networks. Let's jump right in. Okay, so before we start, we should probably know what a GANs is. A GANs could be represented as three people. There is a generator, there's a discriminator, and there's me. Right? And the generator's job is to scribble random things. He doesn't know what they are, right? And send it over to the discriminator. My job is to send actual numbers over to the discriminator, because this is what we're doing. We're working with numbers. So handwritten numbers in this data set. And the discriminator's job is to tell whether those numbers came from me or the generator. The discriminator will get points, meaning it'll get a reward, when he realizes that it came from the right person. So namely, if something came from me, he says it came from me. Real numbers came from me. And if it came from a generator, he says that it came from a generator. And in this way, the discriminator becomes better and better at distinguishing between my numbers and the generator's numbers. The generator, on the other hand, learns how to produce numbers. Namely, he gets a reward when he sends numbers over to the discriminator, and the discriminator mistakes his numbers for my numbers. And in this way, the discriminator becomes better and better, the generator becomes better and better at making numbers that look like mine. That's basically all there is. Let's get to it. All right, so we'll just begin by importing our dependencies. Simple enough. Let's import Tensorflow. Let's import matplotlib. Let's import numpy. And let's import time. Pretty basic. We're going to start off by just importing our images and our labels from the MNIST dataset. We suppose we could use these. Of course, now we have them. Let's plot them real quick just to get an idea of what we have. All right, and we see that we have the number 5 here. It's pretty nice. Okay, so before we start anything, we want to talk about how we want to work with this data. So if we look at train images, right, we can see that these numbers are unsigned integers between 0 and 255, unsigned integers with 8 bytes. 8 bytes, 8 bits. 8 bits. You can't confuse those things. 8 bits, and this might not be a great idea, because if we're going to take if we're going to generate images, they better be of the same type. So uint 8 with 255, or we'll get some weird weird effects that come from the normalization of these things. So maybe the first thing we'd like to do is normalize this and reshape it so that it could fit inside a neural network that we're going to make, right? So first we're going to reshape. And we want to know how many there are. That's that dimension. And of course, the MNIST dataset is 28 by 28 with 1 channel. Okay. And we want to also normalize the data so that the data is between -1 and 1. So that when we put in the random numbers from the generator, it'll actually be the same same type and same range. Okay, and of course this is how we will do that. Great. Okay, so now we need to split this data set. So this data set, this train images is 60,000 images long, and we want to split it into smaller slices with buffer size, and we also want to batch size, and also we want to shuffle it so that maybe the 5s that are clumped together are not together anymore, the 3s that are clumped together are not together anymore, or maybe people wrote this text and there are certain areas of this data set that have certain people's text, which would prevent us from training very well. So we're going to just take slices from train images, and we're going to from train images, and we're going to shuffle with a buffer size. Let's make the buffer size or rather, let's just make it from the size. Train images.shape 0. Right. So the size of the train images, and the buffer size basically just tells us how many of the next number buffer size we want to shuffle from. So if we have, say, 100 different 100 range, so 0, 1, 2, 3, 4, 5, 6, 7, 8 up to 100, and we choose the buffer size 50, then the first number that is chosen in a shuffle data set is from the 50 numbers that we pick, if buffer size is 50. So we're going to choose it to be the biggest so that we get perfect shuffling. And then we need to batch it, right? So how many images per batch do we want? So let's say, I don't know, 100. And now train dataset is an iterable TensorFlow dataset with batch size 100 that has been shuffled from train images. Okay, so we could begin now by making our discriminator model. And the discriminator model is very similar to a normal categorical model that I'm sure many of you have done before with this data set. But in this case, we are only going to output either 0 or 1, or some number between that, which tells you the probability that this number is a fake number or a real number. So is it being pulled from the trained data set, or is it being generated by the generator? So that's basically what the discriminator does. So we're going to make the discriminator model. And the model is a sequential model from Keras. And let's add a few layers. So it doesn't really matter what you do here. Generally, if it's a good model for categorizing these numbers, then it's generally a good model for telling you whether or not it's a digit or not. So we're just going to do something simple here. It's just going to be a few convolution layers, 1 convolution layer and 2 dense layers. All right, so let's do it. So 7 kernels, so 7 filters, and we want the size to be the same, i.e. padding to be the same, and the input shape, input shape to be size 28 by 28 with 1 channel. Right. This is a grayscale image. Great. Okay. Now we're going to add a flatten layer, right? So if we want to take a convolution layer and put it into a dense layer, we need to flatten it. So let's flatten it. All right, very good. Now, to add some nonlinearity, we're going to add a leaky ReLU layer. We could have done that in the activation here, but I decided to put it here. Doesn't really matter. This makes it easier to read. And now let's add a dense layer. And we want 50, and we'll put an activation of ReLU here. Okay, great. Now let's add our last layer. And return model. Great. So let's make the model discriminator. Let's see if it goes through. And it does. Very good. Let's see if it takes in good data. Right. And we see that it does. It's very nice. Let's do it again. Okay, good. It works. In the future, we'll not want to optimize something about it. So let's just add the optimizer. We're just going to add an atom optimizer with a learning rate of 1000. Okay. And of course we'll want to optimize something, so let's define the loss. And of course, a good convention is to always name your functions like they are verbs. So it requires the real predictions and the fake predictions. Right. And the real predictions need to be put through a sigmoid function so that they are between 0 and 1. And the same thing with the fake predictions. So the real predictions come from the real images, the fake predictions come from the generator. Now, the real loss has to be a binary cross entropy, and that'll come from, so the real loss, every single one of these predictions have to be 1. That would result in 0 error. And this has to be the same shape as the real predictions. And the y predictions, y pred, is going to be the real predictions. The fake loss has to be the opposite. And finally, we return it by adding the two together. So that could be our discriminator loss. Okay, so this is the discriminator. Now we want to make the generator. And the generator is a little bit more complicated. What we want from this is to take an input of a random string of numbers and output something that looks like a MNIST digit. Okay, so let's make generator model. So it's also a sequential model. And now let's just add the layers. So we want to take an input that is 100 random digits long and outputs some 28 by 28 image. So let's just first make it a dense layer, because it'll take 100 random numbers. It doesn't necessarily have to be in a array, in a multi-dimensional array. So the idea is that we want it to be at the beginning 7 by 7 and 256 filters, and then we want to upsample from there. So the number of numbers we want from this dense layer, this output, is 7 times 7 times 256. So 7 width, 7 height, and then 256 filters. Okay, and the input shape can just be 100 digits long. Great. Okay, now before we spoke about how we didn't want the numbers here to be 255 because it'll cause our network to overfit for that, right? So these numbers might be very big and then they'll explode out of proportion. So right here, we also want to account for that. And the way we account for that is with something called batch normalization, which in essence just figures out what the mean is of this layer and what the variance of this layer is, and scales this layer's outputs accordingly. Okay, so we're just going to put a batch normalization layer here so it doesn't explode. And we're going to reshape it to be 7 by 7 by 256 filters, right? That's what we wanted before. Now we're going to add our convolution transpose, which is just the inverse of a convolution. The basic idea of a convolution transpose is that a convolution could be understood as a matrix, a large matrix. And if you multiply this matrix by a image, then you'll get output the convolution. If you want to go backwards, it turns out the transpose of the convolution is actually the inverse of the convolution. And so the idea is that taking the transpose of this convolution matrix and multiplying it by this value will output your deconvolution, which is another way of understanding a convolution transpose. So TensorFlow has a nice way of doing this. It's just conv 2D transpose. And so let's input that. So we want it to turn into 128 filters instead of 256. And we want these filters to be 3 by 3. And we want the padding to be same. And basically what this does is just pads the edges so that we don't lose any size. Yeah. Okay, now let's do a batch normalization again. And this time we want it to be 64 and 3 by 3. But this time we want the size, the width and height, which is now 7 by 7, to become 14 by 14. And the way we do that is by adding a strides, right? In a convolution, the strides would decrease the size. But in our deconvolution, it's the opposite. So strides can now equal 2 by 2, which in essence would double the width and double the height. Great. Okay, and again, we want padding to be same. And we can keep going. Everything's good. Okay, now we've done this a few times already. And at this point, we're a 14 by 14 image. 14 by 14 image. We want one more. So let's do that. Upsample one more time. And you guys are pros at this by now, but this time we want only one filter, right? So we want it to be 28 by 28 by 1, not 28 by 28 by 64 or 28 by 28 by 32. We want it to be 28 by 28 by 1. So we only want the grayscale image. So we want 1, and again we'll just do it 3 by 3. And strides, we want it to be 2 by 2 again. So we take the 14 by 14 and turn it into 28 by 28. And the padding, we want it to be same. Excellent. And now we'll just return the model. Okay, and generator, we'll instantiate this model, equals make generator model. And there you go, it works. Okay, now, before we made a discriminator loss, right? But this time we want to have a generator loss, right? It's going to be very similar to this, except this time we'll take the fake loss and we want all the predictions to be ones. So where the discriminator wanted to know whether or not the fake image is fake, the generator wants to know whether the discriminator sees the fake image as real. So the generator will be rewarded when it sees the discriminator misinterpret its image as real. So let's write that. Again, it's always good convention to write a method as a verb. So this time fake predictions. This only takes fake predictions because we don't care what the real predictions are. And the fake loss, we could just copy this from here. Keeping in mind that the fake predictions have to be a sigmoid so that we fall between the 0 and 1 range, otherwise they'll get really big. And of course we want our predictions to be ones. Our generator wants to fool the discriminator. So ones. And we return the fake loss. That's it. Now the generator wants an optimizer, and so we can make the optimizer again. So generator optimizer equals the TF optimizers, an atom, of course, and then we can make this 1/10,000th. Excellent. So now we could go on to our train step. So we're just going to make a little section here called training. And the basic idea is that we're going to make a train step and then a function that uses the train step to go through the training. So we're going to go and make the function that goes through and using the train step first so that you understand what we're doing. All right, so we're going to make a function, and this function will be relatively simple. Right, so we're just going to call it train. It takes in a data set and the number of epochs we want to go through, which is basically the number of times we want to iterate through a data set. Right, so we want to iterate epochs number of times, and in this epochs number of time we want to go through a data set. And to avoid the error we made before, we are going to cast everything just in case images is not of the correct data type. So we need it to be float 32. And the train step using the images, right? So the train step will take images and then improve the models, i.e. the generator and the discriminator. Okay, so this is our train. Now we need to make train steps. A single train step will take only images, right? And at first we have to make some fake noise to put into a generator that'll then produce fake images. With these fake images, we'll produce a fake output and a real output, meaning what is the chance that this image is real or fake? And then we'll have one of these for real outputs and one of these for fake outputs. Okay, so let's just do that first. So the fake image noise is just an array of random numbers, right? And I want 100 of them, but I want batch size 100 of them. So I want batch size number of images, right, that are produced from the 100 random numbers. Okay, and of course we want this to be as type float 32. And then we are going to make a gradient tape. And gradient tape is just basically TensorFlow's way of dealing with gradients. So if we're making a custom training step, we want gradient tape so that we could pull out the gradients and then use them to iteratively improve our models. You'll see how that works in a second. So we're going to call the, we're going to make two of these. One of these is going to be a generated tape, and the other is going to be a discriminator tape. And I'll call it disk tape. So disk tape and gen tape for discriminator tape and generator tape. Okay, now we make the generated images, which you guessed right is using the generator. So using this fancy TensorFlow 2 notation of just functions and not generator.predict with session, we're just going to input our fake image noise. And this will output our generated images. Perfect. And then the real output is going to be using our model discriminator, using the real images, so images. And our fake output is going to be using our fake images, which is just the generated images. Perfect. Now we need something to find the gradient over, right? And namely, this is traditionally called a loss function, right? We defined these loss functions before, so we're going to use them now. So the generator loss is the generator loss using the fake output, right? So we're going to only look at the output of the discriminator if the image's input were fake. So we're getting the generator loss and putting it into gen loss. Okay, now the discriminator loss, we're going to call disk loss, is the same thing, but we're using the discriminator loss. And the discriminator loss takes two inputs, a real prediction and a fake prediction. So it's the real output, which is the real prediction, and the fake output, which is the fake prediction. From here, it's relatively straightforward to find a gradient. So gradients of the generator are equal to the gen tape gradient of the gen loss with respect to the generator variables, but not any regular variables, the trainable variables. So we're going to find the gradients of the generator with respect to the trainable variables so that we use it later for the gradient descent or atom. Okay. Gradients of the discriminator is equal to disk tape, gradient of the disk tape of the disk loss with respect to the discriminator trainable variables. Very similar to what we did before. Now we're going to use the optimizer, right? So the optimizer is going to improve our variables using these gradients. And the way we do that is using the optimizers that we did before. So generator optimizer and the model optimizer, discriminator optimizer. Oh, that's not the discriminator. The discriminator optimizer. There you go. Okay. So the generator optimizer, and we're going to apply the gradients. And we have to zip it so that they're side by side. So there's a gradient and the variable right next to it. And the way we do that is we take the gradients of the generator, right? And the generator variables, trainable variables. So now we have a list, basically, of gradients and the corresponding variable, so that the optimizer knows what to do. Perfect. Okay, and we do the same thing for the discriminator. And for sanity, we're just going to put in some print functions. And if it's not clear, the generator loss is going to be a bunch of numbers. Actually, the number of images numbers, right? So there's going to be a output, which is determining whether it's real or fake for every image. And so we get this number, and we throw it into the generator loss, which produces a number for each of these images. We take the mean of these images, and we can see how bad it's done on average for this specific iteration. Okay, so we'll do the same thing for the discriminator. And that's the game. And so we are just going to run our train now. So using the train data set in 2 epochs. Of course, we get an error. What's the error? Oh yeah. Okay, so it's not apply, it's apply gradients. Okay, that should work. All right, and there it goes. Give it a few half an hour or so, and it should produce some pretty good results. Right, so half an hour later or so, we're going to start seeing results. This is one example. So we input a random number that has, well, 100 random numbers, one image of 100 numbers, and we get this thing that looks like a 9 or a 3, something. Now we can do it again. That one looks like a 2. And I only let it run for around 10 or 15 minutes on my MacBook Pro, which is not the best thing you can do. If you want it to run for, if you want it to be better, you should probably run it on the GPU somewhere, which is totally doable. But on MacBook Pro, you could definitely get some good results. So that right there looks like a 2 or an 8. And that right there looks like a 0-ish kind of thing. That one really looks like a 3, right? Yeah. All right, that's the end of my first video. I hope you guys liked it. If you have any questions about the content or suggestions for future videos, please leave them in the section below. I'll definitely look at them, and hopefully I could do something about them. Also, click the subscribe button so that you could see the future videos when they come up. Thanks, and I hope to see you guys soon.